Okay, thank you. All right, so good morning, and I guess apologize up front. This will be in English. Okay, so what I'd like to talk about this morning is the trends in analog mixed signal products and technologies and some challenges for design. But, that's a huge topic. So I guess I'd really like to kind of focus in on a topic area and talk about some of the things that, some of the areas of convergence that are driving technology. And one of the areas in particular is remote data acquisition. You know, there's a number of, I guess, symbiotic society drivers for the future. More and more interest in personal and health technology, drive for smart buildings and infrastructure, which really leads into pulling in more energy efficiency within those buildings, and there's more focus on energy generation, solar and other distributed sources, and managing the consumption of energy. This is controlling the lighting, controlling the temperature, motion control. All these areas are being pushed ever harder to become more green and more energy efficient. And then, of course, in safety and security, there's again a more push for monitoring the environment. So what you see are examples of the health systems and the many different areas that are getting more and more monitoring, whether from diabetes to the heart and so on. You see focus in the office, again, on the energy management, and, pulling up more smart technology into the boardroom. All of these things are getting kind of tied together by the cloud, and we're seeing more and more need for data and RF infrastructure. And it's possible that one of the things that might lead us into the cloud as a hub is the mobile phone. It's not the only thing, but it's certainly a great vehicle where basically all of the devices, whether for the human interfaces, the vehicles, our machines, could all be interfacing into the cloud. Well, to get this practical, there's a couple elements that are needed, and there's really a common theme that we see within the different market applications. So if you look in personal health and technology, there's a push towards a body area network for data communication. There's a need for low power sensors for doing this biomonitoring. That'll push on analog and for getting precise data outputs. There's a push on data communications, be the RF links, again, back to our hubs, whether it's the phone or some other thing else. To make the systems practical, there will probably require remote data analysis. We can't send back raw data over the communications. It draws too much power. And to make these things last for a long time, it's going to take some form of energy harvesting to basically continue to recharge the batteries. So we're not all plugged into the wall or lugging along very huge batteries. And then probably in many of the cases, there'll be a need to make these implantable, which again drives the power consumption needs. Another application for this data acquisition is structure and environmental monitoring. So, we've got some classic examples of bridge failures in the U.S. That if we had better management and better awareness of the health of the bridge, then we'd have a better opportunity to take preventative actions. And, similarly for things after geophysical events, such as earthquakes, trying to understand the health of a structure, whether it's a building or something like that, to know if it's safe to reoccupy. So within that system, again, there's a push for low power sensors. There's a push for this ultra-low power analog to read these sensors. Again, ultra-low power signal analysis, common theme of data communications, probably RF links, and again, a need for energy harvesting. If we've got all these data acquisition systems deployed, it's very difficult to run wires, it's very expensive, and pushing RF is really needed. And again, the same issue with energy harvesting to have long life sensors deployed. And then taking it more personal in a smart building where we're trying to reduce the power of the building, having intelligent ambient low power sensors to detect occupancy, to detect temperatures, to basically be able to control the building for maximum energy efficiency. Still need the data communications and RF, and possibly wired, but I think RF again will be the easiest to deploy. And again, to make these things last a long time, energy harvesting is another recurring thing. So this is going to be a strong direction for a lot of market applications, this whole notion of remote data acquisition. So talking about what we're doing in wireless, you know, already there's a lot of wireless deployed in alarms and security applications, whether it's fire alarms or proximity sensors. We do have solutions for RF. They tend to be heavily point-to-point kind of solutions, and this is something that really is going to take future addressing. You know, in our remote controls, the RF for consumer electronics is an area that's focused. And again, same need on the power. You know, this is another great example of remote power requirements, because who wants to change the batteries in the remote? We have to get up. Then wireless audio, of course, you know, to get streaming audio. And then sport and human interface devices. Again, push for very long life of these consumer applications. And then smart metering, the focus on Zigbee and narrowband communications. Again, heavily point-to-point today, but something to be addressed. And then home automation lighting. You know, this is kind of where we're beginning to see the appearance of Zigbee and, you know, low sub-gigahertz transceivers. And this is a good start, but to be honest, I think that's an area of challenge too, because there's a limit to how many nodes we can get on the mesh network and how flexible they are. So when we talk about the elements of a wireless sensor node, I think the themes are pretty obvious. But the cost of deployment or changing batteries is a big deal, and it has to be driven down. We need to reduce costs of the sensors. And then as we build this system, you know, there really needs to be a standards that goes in so that they're interoperability with the existing wireless standards. Can't interfere with existing wireless standards, but also need to be able to talk with each other from different manufacturers. So really a multi-standard support is going to be required. And so really what we're looking at is some sort of multimodal sensor support. You know, there's going to be, again, driving towards flexibility, we're going to have a system that can easily be deployed and work with multiple sensors. It's got to be secure. It's got to be able to wake up and drop, and it's got to be able to detect if it's call it a friendly device on the network, or if there's some sort of interferer that needs to be dropped. And these devices really need to be configurable from a master slave or both. And of course, the drivers is cost, size, and how long these things can last. So it kind of pushes us towards some sort of self-sustaining energy. There's multiple sources of energy that are going to power these devices. A primary battery is going to be really the #1 source, so the thing can stay up regardless of conditions. But nonetheless, to make these things last longer, we need some sort of energy harvesting to boost the power back up. And so to drive the size, we need some sort of high-density storage, some chargeable battery, or maybe a supercap, and to be able to reclaim the power. And of course, these devices can't fail, and they need to be coming up and be always on and always aware. So again, driving the energy efficiency, they be able to sense and continuously, and smart in their communication, so they only connect when they deem necessary, because the RF power is really a big source of load on these devices. So they're going to need to be able to drive some sort of compressed data. So what this really pushes to is, again, remote data analysis to make these devices work. And then when they got to be able to hibernate and be able to turn down and retain the history at the whenever there's some sort of data loss. They can't just disappear and not come back up again when power comes alive. So here's kind of an example of a start of this system, and this is basically an RF transceiver that is designed to work with one of our microcontrollers, the MSP430 and the CC2500. And this kind of helps provide a picture of where we are and helps give a feel for where we need to get to. So the CC2500 does already run on a relatively low supply, 1.8 to 3.6 volts. It sleeps at less than a microamp, but when it powers up, it's running 1.5 milliamps, and when it's transmitting, getting ready to transmit at 7.4 milliamps, and when it's receiving, it's 15 milliamps, and the transmit current is 21 milliamps is the device specifications. So it's pretty clear that we want this guy to sleep a lot of the time. The MSP430, pulled for this example, again, has similar supply ranges, but it has particularly good sleep or standby current. It's 0.1 microamps for sleep current, 0.9 microamps for just the real-time clock operating. So we can get this guy running at, some 3 microwatts, relatively low power. When the device is ready to go, it's 90 microamps, but really when it's running, it's about 400 microamps that this thing's drawing. So if we kind of look at what this means in a system, this is a kind of a typical curve, but if we had some sort of sensor that was running, and depending upon the sensor rate, 10 hertz, 100 hertz, or kilohertz, this is kind of the anticipated sensing power, and this is something like a 16-bit A to D converter that would be turning on and turning off. And so the idea is basically we're running around 3 milliwatts at a kilohertz, but we can duty cycle that, and we can get down to 33 microwatts at low data rates. The microcontroller is actually doing better than the data converter, and so we've got 60 microwatts at a kilohertz and 2 microwatts at the low speed, and then the radio. And for this example, what we assumed was that there'd be like a one-day burst out of data collected, like thinking about the environmental safety or a health monitor for a building or something like that. It doesn't need to be communicating all the time. So that makes it practical to have a daily update. And if an event occurs, then it could also be updating. So the average radio power would be a couple microwatts. And so the net effect, as you can see, that the total average power, depending upon how fast we drive this, is 37 microwatts at 10 hertz data acquisition and 3 milliwatts at at faster times. So you can kind of see that the long pole in this is really about what we can do about the sensing power and a little bit less about what we can do about the microcontroller, although there's some opportunities there. So figuring that we have a 500 milliamp hour battery, we're looking at a range of lifetime from maybe up to 5 years down to just a fraction of a year. So this is really problematic. And what we looked at and took on the objective is to basically reduce the average sensing power. So really knock down by maybe a factor of 20 what we're doing in that data converter and the sensing elements. And so we'll talk a little bit about that in this presentation. There's continued advances in the microcontroller power, and we'll talk a little bit about that. And the radio, you know, we are kind of limited by physics. There actually is some improvements going on here, but we just assume that to be fixed. But if we do a good job on the sensing, we can really move our battery lifetime of this 500 milliamp hour battery out to 30 years, which probably isn't practical. The battery will probably die by then. But certainly what we're doing is we're getting down to a case where the power will be low enough that energy harvesting becomes practical. And it's kind of problematic for a size area up here. So here's what we're seeing for our vision for a wireless sensor node next generation. So what we're looking at is basically a chip that has a sensor interface that we can measure the real world with: pressure, temperature, acceleration, potentially ultrasound, again, thinking about physical analysis, strain, or other transducers. So we really have this analog front end that we need to work on. We continue to leverage a ultra-low power microprocessor core. There's some opportunities for improvement there, and we'll talk about some of the things we're doing. And then we need to have some sort of local power management and regulation and the ability to do some energy harvesting. And then we need that RF communications on chip and putting together this into a technology. So talking about the energy harvesting sources and the technology available. Vibration is a modest source of input. You know, if a body moving around maybe is about 4 microwatts per centimeter, maybe, or centimeter cubed. In something that's done in industrial, maybe you could get a little bit better, up to maybe 100 microwatts. So maybe this is pulling off of an engine or something like that that's already in motion, or a motor. But a temperature delta, where we can basically make voltage leveraging the CVIC, we can get up to maybe 25 microwatts per centimeter. Again, checking temperature, but frankly, I don't think many of us will enjoy wearing something like that around. It'll always feel like we have some sort of cold object on us. And then, but industrial, again, the heat of things around us actually becomes practical, and seeing at 1 to 10 milliwatts per centimeter cubed. And then on light for solar, maybe we can get 10 microwatts, and outdoors we can get 10 milliwatts. So solar is pretty practical as long as it's not a getting issue with dirt and other contaminants. And you know, we looked at RF. Can we pick up RF energy? And you know, frankly, it's just not practical. You know, that we'd be able to collect RF sources. So here's some work that we're doing within TI on the energy harvesting. So this is a ultra low power energy harvester that uses just 100 nanoamps-ish of power at the low state. This is the BQ2504. It's something we've been developing and is now available on the market. But basically, it's got the ability to connect to these different energy sources, particularly whether it's solar or kinetic. It can ramp to a startup from as low as 400 millivolts of a source and then run down to as little as 100 millivolts. And so this is a device that can start up from nothing with no power and be able to then store its energy output onto a capacitor, some sort of thin film energy storage, or a rechargeable battery. So this is a device that's coming together that's pretty practical as a circuit implementation that as we advance our nodes can easily fit into our needs. And just an example of a lithium-ion battery, so the 2032, this is a device that lithium-ion is 40 milliamp hour, is chargeable. This is plenty of backup power to keep our devices alive as long as we have some sort of regular energy that we can harvest. So let's talk about the microcontroller a little bit and about some of the work that we're doing there. And this is kind of a contrast in computation, that basically the high-end computer microprocessor really needs much faster performance and also much greater energy. And when we get into the ultra-low power systems for control and local data analysis, we don't need that much computation, but we definitely need very little energy. So the battery that's required to support these systems really goes from 100 watt hours down to somewhere to 1 watt hour or less. But interestingly, the energy efficiency is dramatically improved in the ultra low power case over what we get in the server or laptop CPU, where basically we're getting 10 to the 9th computations per joule, and we get 25x or 25 times 10 to the 9th computations per joule in our ultra low power MSP 430. So from a battery lifetime, I think we're all living it. I certainly do on every intercontinental flight. We say a day, maybe it's a handful of hours that we get 8 to 10 hours of battery life, whereas for the microcontroller, we're really getting out to about 10-year kind of battery life on very low power. Again, the whole notion that we've got to be able to keep these things powered up. So what's affecting this and what's driving the technology? We'll go through and talk about some of the process and some of the circuit solutions that we're doing to optimize the life. So from on the digital CMOS power, there's really two key areas of power that we need to focus on. It's both the active and the standby power. Because these guys need to sleep, they need to have very low down current, that's why the standby is so big. But on the active power also, we need to minimize the power usage to get the maximum output. So the active power is really driven by the change in the output and the charge and the capacitance that we need to drive as we go from gate to gate. And of course, the faster we switch. So, this is kind of a well-known expression. The dynamic power is the power that's in the switch during its switching times the supply voltage squared times the frequency, the capacitance load, and of course, how many of these we got. So the dynamic power consumption really pulls us down to kind of a speed analysis that we need to optimize, where we need the to get the maximum speed is basically the on current of the device divided by the supply and the load. And so what we want to do is we want to make the devices as minimal as possible so that we can drive the load capacitance as small as possible. And so really what we want to do is kind of twist it so that we can set the supply voltage according to the maximum desired speed of the gate without building up the device, the drive strength of the gate. So this is some active control. And also this way the gate leakage scales with the supply voltage. So here's an example of that F max. As we vary the voltage, it certainly rolls off, but we want to basically minimize our voltage to minimize our power based on what's required for the computation. As I mentioned, the other source of error in these systems is leakage, or the standby power is critical. And for that matter, even when we're running the devices, we want the devices that are supposed to be off to be switched off. So the sources of leakage are classically the drain leakage, the junction leakage, sub-threshold current. So basically when we turn the device off, how much current still flows. So I-off current. But really a new error that's coming up for our devices is gate leakage. As these gates get thinner and thinner for submicron, we start losing more and more power through the gate. So it's really changed how we affect this. So so our net is our formula for the static is really all about the leakage of the junction and leakage of the gate. So what we're really looking at is to see if we can affect the power dissipation by affecting the threshold voltage to change the leakage, and looking what we can do for the subthreshold voltage slope. So, classically what we've been doing is optimizing our process technologies for speed, but now this thinner oxide's increasing the tunneling leakage currents. The higher temperature further exacerbates this because the leakage goes up at temperature, and if things aren't completely shutting off, as we increase the functionality speed, it just gets worse. So, we can take some advantage of reducing the supply voltage, and that helps at the high end, but it doesn't help at all at the low end where we're trying to turn these guys off. So this is a comparison of the logic power versus the technology in the node and how things have been moving as we progress to finer nodes. So what you see is a dramatic movement as we go from a 130 nanometer process to a calculation as we get to finer and finer process geometries, and now the static power is coming up to meet the dynamic power. Sure, we're getting benefits on the dynamic power, but now the off current and how long these things are going to last when they're idling or sleeping is becoming dramatically an issue. And the power per chip for standard VT is becoming is also can be helped a little bit with supply voltage, but it's problematic. So the frequency of operation does also kick down dramatically, as we talked about even earlier, as we lower the supply voltage. So it's really playing against this trade-off of speed, power, and of execution. So what you see is that this push on the active leakage power, we really need to reduce the off current of the device is a key parameter for these remote data acquisition. For a large microprocessor, no big deal, but for our systems that are being put out in the field, it's a huge deal. So it's a driver. So the dynamic power scales down with the node, but the leakage power gets worse with the node without doing design tricks. To be sure, we do some design tricks in terms of trying to turn off supplies that aren't being used, but even these come with their own overhead. So what we can do is take advantage of threshold voltage to reduce the off current. There's only so much we can do gate leakage, but we can improve our off current. So with decreasing supply voltage, you know, we can reduce the on current, but again, can't do anything about the off current. So ideally what we'd like to do is figure out what we can do to manage this. So what that drives us to is to rethink about what our requirements are for an ultra-low power data acquisition process technology. And so ideally what we'd like to have is two types of transistors. What we want to have is a fast transistor that can help us for the speed requirements, but then we also want to have, wherever we can use them, slow transistors that can minimize the off current. And so that's something that we work on, is actually creating that very device. So we work on reducing the supply voltage, and we work on reducing the threshold voltage to reduce that leakage. And so that's one of the things that's driven in our new technology, is this capability to have simultaneous a low leakage and a high-speed technology. So that's kind of what we're doing about the standard CMOS. Now we also need to address the memory. Flash memory is a workhorse technology that we've had. It's got really good read speeds. It's a very dense bit cell, but the problem with it is that the floating gate memories need high voltages to write. So it takes power to write to this device, because we have to run a charge pump to pull it up to basically be able to set the charge underneath the gate. And it's slow for these write and erase. And actually, every time we do this, we're degrading the oxide every time we write to the device, and it reduces the endurance. So we've developed a technology at TI that we call FRAM. It stands for ferroelectric random access memory. There is no ferro in this. There's no iron. But it behaves sort of like a polarized magnet, so that's why we use the term FRAM. And what we have is we create a bit structure that's not unlike an SRAM, where we basically have two sets of differential capacitors, or we could have either at a common reference for a 1T design, 1C, 2T, or we can do a 2C, 4T. But the idea is that basically we have a capacitor that is polarized. And so essentially this is a lead oxide cap that's got a moving ion inside. And so depending upon the last write voltage, when we do a comparison, it moves the ion if the previous value was a 1, and then we're reading it, we check to see if the previous value was a 1. If it was, then the amount of charge required to read that 1 is very little. But if the previous value was a 0, then it takes more charge to read that one, and hence that's how we store a 1 or a 0 and read it back again. So it's a destructive read, but then we just quickly write it back again. I hope that makes sense. If not, see me on the break. But this, what's really cool about this is that this is an enabler to get a technology that can run on very low power supplies, because now we're no longer needing a charge pump. We can just run this on standard supplies. It doesn't read quite as fast as flash, but it writes a heck of a lot faster than flash. And the write current is as low as the read current. And it's just a capacitor with a moving ion. Theoretically, the endurance is infinite for these devices, and that's key. And as far as a process technology, it's relatively simple. It's only a 2-mass scatter, because basically what we need to do is we need to lay down this piezoelectric, and we need to lay down the top of the cap. So if we compare it, technologies for the FRAM, of course, for non-volatility, does the device retain power? Of course, an FRAM does. It's a polarized cap. It'll stay theoretically indefinitely. Obviously, an SRAM does not retain a data power. A double EEPROM, of course, does, and a flash does. Looking at the write speeds, and this is just an example of a 13 kilobyte memory, the write to an FRAM is 10 milliseconds for the 13 kilobyte block. An SRAM is probably a little bit better than 10 milliseconds. You know, the caps probably can be a little bit smaller than what we're using in an FRAM, but a double EEPROM takes a couple of seconds. We've got to boost the thing up, charge it up, and then write to it. And flash, you know, certainly there's efficiencies in the implementation to make it more RAM-like, but it's still orders of magnitude greater than what we get out of the FRAM. The active power, where we're reading and writing to the device, is 82 milliamps, you know, just a bit over what you get out of an SRAM, again, because of the size of the caps. An double EEPROM obviously takes up to 10 milliamps of power as you're reading and writing. And flash can take up, it certainly gains some efficiencies. And as mentioned, the write endurance is dramatic for an FRAM. You know, we really don't know where they break. They last a long time. Double EEPROMs obviously have a maximum lifetime, as well as the flash, as we degrade the oxide. And, you know, it feels a lot like an SRAM, bitwise programmable, because you only have to write to 1 bit, like an SRAM. So, very easy to implement. Okay, and I'm an analog guy, so I got to talk a little bit about some analog stuff in this. And this is some of the work that we've been doing on low power references, again, to realize that analog solution. So traditional band gap, and this is pretty darn classical. The band gap voltage is equal to a VBE of a bipolar transistor plus a gained up error source. So we basically run differential current densities, creating a delta VBE that we then gain up, so that we get this band gap voltage that's VBE, which has a typically -2 millivolts per degree C, temperature coefficient, and then add it to a positive TC that's made up of this delta VBE, and we get to about a 1.2 volt output voltage. It's a classic circuit. It has errors, of course. The mismatch of the resistors cause current source mismatch errors. The VOS and VOS drift of the input of the amplifier cause errors that all affect the band gap voltage. And of course, it's a little bit hungry, and it takes in power and resistor area. So this is an area that we've addressed as well, is improving the band gap reference. And also, you know, as we run some of these lower voltage devices, we'd really like to have a lower voltage reference. So what we've come up with is a reverse band gap. Previously, we were taking a VBE and we were adding delta VBE, a multiplied delta VBE to it. In this case, what we're doing is we're taking that VBE and we're dividing it down first. So we divide down the VBE with a capacitor divider, saves on area and power. And so when we on this switched reference, what you see at the end of the first sample, we've got these capacitors reset and then charge them up with the add of a current. We get a divided VBE that, of course, is C over C plus the sum of the C's. On the second phase, what we do is we basically boost the current by a factor of n and float this node, and the net effect is the delta VBE of this guy will juice up by the VT natural log of n. So it bumps up, and the net effect is we now have our band gap that is a divided VBE plus a reduced gained up or reduced VT natural log of n. So now we have a 200 millivolt output band gap, much more useful for low voltage circuits. So this is kind of what the actual device looks like. I won't go through the whole thing, but this is the setting up the currents and then setting up the switching for this delta VBE. It's a relatively easy device for us to implement and manage. But we can do more with that. We can also not leave that guy switching all the time. Okay, so what we can do is we can, after we've generated our reference voltage, we can then sample it on a capacitor and keep it running for a long, long time. Now, this is, if we have an ideal switch, no problem, but we don't have an ideal switch. So what we do is we make a composite switch network so that basically we can drive the leakage of the switch with an amplifier. So here's our sample and held output by contrast. But now this is a device that can get a very, very long time held value of VREF that we can then buffer with a follow-on op-amp. And you know, we get into the power down to 0.2 microwatts for this reference. So that's a real enabler for our system. And being a data converter guy, I need to throw a data converter in here. And actually, again, this is kind of the long pole in our tent. So we've implemented a successive approximation ADC, a 16-bit ADC. And one of the issues that we have in ADCs, particularly the SAR ADCs, is when we sample, we need to sample on some sort of midpoint voltage. Because as these guys are doing the bit comparisons, it's very possible with an input voltage that goes up into the supply that we can actually switch and we can have the inner capacitor network of our ADC exceed the supply voltage. And this is a real big problem because then we lose charge and then we get an erroneous reading. And so depending upon the speed of the device, this could be 100 milliwatts of power down to hundreds of microwatts, again, based on speed, but it's a huge limiter for what we implement. So what we came up with was this scheme, where we switch the polarity of our sampling of our input. So as we switch through the networks, we initially sample to the opposite side of the other CDAC array, and then when we go to the convert mode, we switch it back, and the net effect is that we can cancel the common mode voltage immediately. So now we've got a zero common mode voltage that we can then do switching with, and we no longer get errors that go above and below the supply. And we no longer need to keep a buffer on all the time, so it's a true zero power sampling, ready to go all the time. Switches on the input take minimal power. So, hope I didn't bore you too much with the circuit stuff, but I just felt obligated to stick a couple things in here. So, and I guess I want to comment that one of the things that we achieved with this circuit was we got our power down to less than 10 microwatts for a 16-bit ADC, far better than at running at a kilohertz, far better than the 300 microwatts that we were showing earlier for something similar, or 3 watts. So with that, let me kind of wrap up the talk, and is that, you know, the wireless sensor nodes are coming. The drivers are there in society, and we basically need to rise to the challenge to figure out how to address them. And I hope I gave you a feel that the solutions exist, or they're near and coming, in the low power microcontroller. We're driving down the power of the microcontrollers. We're reducing the power of the analog. We are working on lower power RF as well, but depending upon how fast you sample, that's not that big of a deal. The energy harvesting is radically improving, and certainly within TI, you know, we've been developing the process technology to support this ultra low power system. So next thing's coming up is integrating more sensors onto our system, onto our chip, and also reducing the power of those sensors. And I think the big wart that's coming out there is the infrastructure for the data connectivity has a long ways to go and needs to mature quickly to enable this. So thanks for your attention, and